Hi everyone, this video is for lesson 1-2 and it's part 2 of the lesson. So yesterday or in your last lesson video, we discussed the difference between undefined and defined terms. Today we're going to continue and talk about how postulates affect geometry. So first, in order to discuss how they affect geometry and what they mean for geometry, we have to define what a postulate or an axiom is. So if you hear us say postulate, or you hear us say axiom, they essentially mean the same thing. Now, the first thing about a postulate um, is that a postulate is something that we accept without it being proven. So a postulate does not need to be proven. So I think of any statement in which I just accept what someone tells me. So for instance, I think we've accepted as a community that the sun, or I should say that the sky is blue, right? That doesn't need to be proven. It's almost obvious to us. Like we accept that statement of fact. So a postulate does not need to be proven. What we consider it is an accepted statement of fact. Does not need to be proven. It's an accepted statement of fact. Um, the way I like to think of it is almost like a counterexample. So something that you have to prove to someone. So I think of possibly going to the courtroom and having to prove your case, right? If you say to the judge, I'm innocent, chances are they're not going to just believe you unless you could prove that you're innocent. You made a statement, but you need it for it to be proven in order for it to be believed. But something that does not need to be proven, like the sky is blue, we just accept that statement of fact. So a postulate, again, does not need to be proven, we just accept it. So then why do we need postulates in geometry? It almost seems like if we're talking about the sky is blue and talking about the courtroom and trying to prove something, why do we need postulates? And actually, postulates are the building blocks of geometry. So in geometry, we have something called a logic system, right? A logical system. We build upon something. So we give a postulate, and from that postulate, we have all of these other facts and ideas that come from it. So without postulates, we essentially don't even have geometry. So they are the building blocks of the logical system in geometry. Okay. So now that we've discussed essentially what a postulate is and why we need them, we're going to talk about some postulates. And for postulates, we really have postulates by number. So the first postulate is postulate 1-1. And this postulate, there's this diagram over here that kind of shows it, but I like to kind of show you an example. So for this postulate, I'm going to put 2 points on right here and here, so these 2 red points. Now, given these 2 points, I can only draw one line through those 2 points. So there's my line. Only one line can go through those 2 points. I think we would all agree. Right. I can move this red point up here, so change its location, and still only one line goes through these 2 points. So no matter any location of those 2 points, there's only one line that goes through those 2 points. So postulate 1-1 simply says that through any 2 points, so any 2 points that you have, there's exactly one line. So through any 2 points, there's exactly one line. So over here, it just says that line T passes through points A and B. Line T is the only line that will be able to pass through points A and B. Right? No other line can go through points A and B except line T. All right, so let's take a look at postulate 2. So postulate 2 is, let's kind of draw this, and then I'll draw this. Now I'm going to ask you how many lines did I draw, and if we're going to be a little more even accurate here, I could even put arrows at the end of my lines, right? And while I'm adding the arrows, kind of think to yourself, how many lines did I draw? And I drew 2 lines. Now, I drew 2 lines, and how did they intersect? And another term or another way to think of intersecting is by crossing. So intersect, cross. So where do they cross? Or touch, right? All of those verbs could be used interchangeably here. So where do or how do these 2 lines cross or touch? And you probably say, well, Miss M, it's right in the middle. They touch right in the middle. Good. So where they touch or intersect, what have they formed? And right in the middle here, well, they cross at a specific point. So now we say, all right, well, 2 distinct lines, if they intersect at only one point. So if you have 2 separate lines, when they cross, they're going to intersect at exactly one point. So 2 lines intersect at exactly one point. So here, you have your 2 lines, line AE and line BD, and they intersect at point C. So that's postulate 1-2. Postulate 1-3. Now, this is a little hard to visualize here. But you can kind of think of it almost as like a piece of paper, 2 pieces of paper that are almost like creating an X. So since they're plain, they kind of look like these rectangles, and they're different colors. One's plain RST, and one is plain WTS. You have your blue and your yellow. And if you look at how they cross, they intersect right here. And they almost intersect, looks like a segment. But planes, remember, go on forever. So planes never intersect at a segment. They always intersect in a line. So for this postulate, it says if we have 2 planes, they intersect in exactly one line. And I'm going to actually make note of that over here. Planes always, if they planes go on forever, so they intersect in a line, not a line segment. So even though it looks like they stop, they don't. They go on forever because they're planes. So those are the 3 postulates to start, and we are going to continue by turning to the next page. And let's see what we have now. Now we have some practice. Okay, we're going to see if we can kind of figure this out. So it says we're going to use this diagram to the right, and it says each surface of the box at the right represents parts of a plane. So it's a part of a plane. They first want to know what is the intersection of plane ABC and plane BFG. So remember, the 3 letters ADC, so ADC, are just points on what plane. So if I go from A to D to C, I'm beginning to form the top, right? And then I have plane BFG. Let's see where that is. Plane BFG, BFG here. So if I continue, where do the 2 colors overlap? That's the intersection. Now they're planes. So we know planes intersect in a line. So what line do they intersect at? Well, to see what letters they overlap at here at BC. So they intersect at BC. And remember, BC is a line, so we have the little hat on top that gets the arrows. And we change this to some arrows. 1, 2, there we go. Okay, so now let's try the next question. What are the names of the 2 planes that intersect at BF? So I'm going to look here. I'm going to delete and delete. So we have BF, and here I'm going to highlight BF. It goes up and down. So what 2 planes intersect at BF? So BF would then have, let's see how we can figure this out. So what 2 sides, when I connect them, would overlap at BF? So I know this has to be one side, and then I can kind of form this plane over here. So I'm going to name this plane ABF. Remember, you need 3 letters in the same order. So if I go from A to B to F, that's a good way to name this plane. I couldn't go A, E, B. It has to go in the same order. So I'm going to go to the right, A, B, F. So here, I have plane ABF. And where else? Oh, it looks like this back here, so I'm going to highlight it, right, because it has to overlap. So now to get the green to overlap with the blue, we draw like this. And now we have maybe GFB or CBF, however you would like that. So ABF and plane, maybe CBF. And there's that. So that's where they intersect. Okay, so now B. Why do you only need to find 2 points in common to name the intersection of 2 distinct planes? Now, if you think about what postulate 1-3 actually says, it simply states that 2 planes intersect in exactly one line. So if they intersect in exactly one line, to form a line, you only need 2 points. So that's really our reason. So we're going to write 2 planes intersect in exactly one line, and then we know you only need 2 points to make up a line. You only need 2 points in common because if we're trying to name the line in which they intersect, we only need to find those 2 points. That's what postulate 1-3 says. Okay. And down here, we just kind of remind you that when you name planes, like the one above, you have to list the corners in the consecutive order. So you have to go in the same order. So either like clockwise or counterclockwise. Go to the right, go to the left. And up here, we kind of gave you that example, right? So we said, like, if we were naming this top plane, it could be A, D, C. It could be A, B, C, D. It can't be D, B, C, A. That's not in the same order. You have to kind of go around the figure. Okay. Now I like this down here, and this kind of explains the last postulate for today. And it's kind of like the use of a tripod. So if you've ever used a tripod or have been around one, often it's used in photography. And the reason being is because the 3 points, right, these 3 points on a tripod, will always touch the floor at the same time. But if we added a 4th point, it wouldn't always touch the floor with the other 3 at the exact same time. And I think of this as like ever go out to dinner or even sitting in a chair or at the desk, and sometimes it's a little wobbly. You'll never sit on something that has 3 legs and it be wobbly. As soon as you add a 4th or even 5th leg to something, it's potentially could be wobbly. And there's a reasoning behind this. And the reasoning is the 1-4 postulate. And that says you only need 3 non-collinear points to be in a plane. Once you get a 4th point, it potentially could be out of that plane. So this says here that you only need, or there are exactly 3 non-collinear points that could be in one plane. So 1, 2, 3, 3 points are going to make up this plane here. Once you add that 4th, it could be on the plane, but it also could not be on the plane. Now, the key here is that they must be non-collinear. So through any 3 non-collinear points, there's exactly one plane. So we're picking points R, S, and Q, and that is the last postulate for today. So let's try postulate 1-4, and we're going to use this over here. So they want to know what plane contains points N, P, and Q. So we have N, P, and Q. So if and then it says the color. So I'm going to kind of connect N, P, Q, and think about what plane these points would be on. If I had to make a plane, right, and the plane looks like a rectangle in terms of us sketching it, I actually can form this plane on the bottom. Right, and this plane at the bottom is the plane that they all lie on, and here it is. So we're going to name this plane. I can call it plane maybe RNQ, sorry, RNPQ, or I can call it plane, they use 3 letters, even NQ, right? I can't call it RQP, that wouldn't work. We have to remember be consecutive. So NPQ, RNPQ, any of that works. Let's try this one now. What plane contains points J, M, and Q? So I have a new diagram, and I'm going to kind of work through the same way. J, M, Q. So I like to just go from J to M. Now look at Q. It's only down here. This is awkward. Let me just connect J M to Q, and it looks like it's actually going to be this diagonal plane. And that's possible. I can kind of slice this going diagonally from this edge through to this edge down here. I bet you didn't think that that could happen, but it can. Because remember, a plane is just any flat surface that extends infinitely in any direction. Here it is. Ooh, I like the way that looks. All right, so let's name that plane now. So this is going to be, first, let's kind of get this. This plane is diagonal. This is a diagonal plane. It goes on an angle. And we have this as plane. We can say JMQP. Or if you just want to use 3 letters, what if we just call it JMQ? Or even PJM or PQM, right? 3 letters in any consecutive order. So plane, change it up. Let's do PQM. We have it. Okay, so why don't you pause this and maybe try this one by yourself. And I'm going to go through it, but you can pause and certainly try it by yourself. So now we have L, M, and N. So remember, I kind of find my 3 vertices, my 3 points, and I connect. And I try to figure out how am I going to form this rectangle by connecting one more, and that's going to be right here at P. And then I color this in, and yet again we have the diagonal plane. Let's name it. This is going to be plane. I'm going to use 4 letters and then 3 letters. So plane MLPN or plane MLP. Okay. Right. And then finally it says, what is the name of the line that is coplanar with both J, K, and KL? All right, so I'm going to go here. So we have JK, there's JK, and KL. Okay, so remember, coplanar. So here are the points, J, K, and L. As to make a plane, I'm going to go across the top so that all 3 are on there. So here we have our plane, the top part of our prism. Now it wants to know what's the name of a line. So what line is coplanar with this? So we could say line ML. We can say line JM. So I'm going to say line ML. If it's coplanar, it has to be in plane. JM. Okay. It has to be in plane JM. Okay. And there we have it. Okay. So that really finishes up the lesson. For right now, if you would like, you can kind of look through these questions. We're not going to go over them right now. We may add a video or possibly upload the answer key. You're not required to do anything with these questions just yet. But these are good like questions to check to see, did you understand what we just went through? Maybe go through them and just ask yourself, can I answer these questions? Okay. If you have any questions with this lesson, as always, feel free to stop by.